Welcome to the October 2020 edition of the Atlanta Radio Club monthly meeting. Thank you for everybody for joining us tonight. We got another great speaker in store for us. So thank you for joining us for that. And also, we'll go ahead and Stephen, our repeater manager, was going to go ahead and give us a quick little monthly update on our repeater stuff. So I'll give it to Stephen for that. Go ahead, Stephen.
All right, so we have the new controllers in, and I've been programming them. And so at this point, I think the next step is to get some cables ordered, which Jeff told me he was working on. So as soon as we get that done, then we can go up and deploy everything. So I think that's about it. Other than that, nothing really to report.
Okay, yeah, we're gonna have to be doing some probably some maintenance here when we get an opportunity to. It's real difficult to get up on the top of the bank tower right now with all the security stuff in place. So we're having to kind of do this a little at a time. So thanks for that, Stephen. We're going to have to do some maintenance coming up because there's a lot of stuff up there that's been up there a while. So a lot to come. Stay tuned. And if you have an interest in being on the repeater committee, please do contact one of the club officers. You can email us by any one of our titles: president, vice president, member at large, secretary, treasurer, and it's at atlantaradioclub.org. And just let us know that that you're interested in being on the repeater committee, and we'll contact Stephen and let him get in touch with you. He's always looking for help. So activity wise, we've got several things coming up over the next 12 months. The board met a couple weeks ago, and in the next couple of days, we'll have a finalized calendar out of things that we're going to aim to do over the next 12 months with specific dates. There's been some discussion on defaulting to second Sunday when possible, as we used to do the second Sunday tech session and the Sunday in the park type stuff. So if there's not something specific during the month, then we'll default to the second Sunday, but that'll be on the calendar so that you know over the next 12 months what we're doing. And of course, we always add a few things here and there as we go when we find fun things to do. So only thing that I need to let you know of right now is next weekend, the 15th and the 16th, is the 50th anniversary of the Stone Mountain Highland Games. And I kind of volunteered us to hopefully put together, it's real short notice, but a special event station out there. We'll see what we can put together and do. So if you have an interest in the Stone Mountain Highland Games, if you've ever been to them or have heard of them before, it's a ticketed event. So I really need you to sign up. I'll check the email, the IO group. I'll be putting out an email tonight with a sign up sheet. And that way I can get tickets accounted for to get us in the gate. So we're going to be working within the venue. And that's why I need to know who exactly is coming. Plus there'll be a t-shirt involved. It'll be a 50th anniversary t-shirt for the Highland Games for the special event station. So everybody loves a t-shirt. So keep an eye out on the email for that. And that's next weekend, not this weekend, but next weekend. And then, like I said, going forward, we've got a holiday party coming up in December. We're working on where we're going to be and what we're going to be doing for that. Last year we did the Mad Italian in Dunwoody, and that was a great time had by all. So we'll do something again like that at a restaurant. So please do kind of put that first Thursday of December on your calendar for the club party. That's it for right now for me. I'm going to go ahead and turn it over to our dashingly handsome program manager, Rob, KI4UTY, and let him get us rolling on our program tonight. Go ahead, Rob.
Sounds good. Oh, there's also Stone Mountain Ham Fest is coming up.
Oh yeah,
next
first
month.
weekend in November.
And we're gonna be there. So tonight's guest speaker in our series of wonderful guest speakers, which I'm pleased to announce. I'm pleased that we've been able to do that. You know, since we can find speakers from around the country instead of just in the city. I found a wonderful bunch of people to speak over the years, and continuing that tradition. We've got Michael Burnette, AF7KB, And he is an author, as he says, he's an award-winning author of the best-selling Fast Track to Your Ham License series. He produces YouTube videos on different aspects of ham radio. That's how, in fact, that's how I found him. I was doing a search for antennas, and I found his, and I started looking at the video. Said, "Oh, I need this guy." And he's just got all kinds of things going. He's teacher, and as he heard, he loves having people get licenses. How can you get better than that? So, and that
We got our computer updated, and once we got our computer updated, we was able to run the software.
where's that coming from? Oh,
That's Canon N4CBT.
okay. All right, let me get back to where I was over here on my thing. Yeah, so Michael, Michelle is our newest member on here. So as you heard, she's looking forward to it. So I'm going to turn it over to you, and please do your magic. Over to you.
Thanks, Rob. And Michelle, I hope I won't disappoint. I've been keeping my eye on Bob, KC4BI there. I'm just a little nervous about what he's going off to bury. All right, let's see if we can get this thing rolling here. Should be this, and it's not. Let's see. Screen sharing has stopped. Now let's, oh gee. Suddenly all heck has broken loose here. Stand by. Get this working. It was all set up, and then I think I jiggered something, and you know how that goes.
No, we've had some weird things happen on Zoom, that some of them I did. So go ahead.
It's just not showing up as well. Let's see. I think you guys are seeing my presenter screen, right? What are you seeing? Like a PowerPoint screen with an orange bar at the top? Or are you just seeing a black screen?
Screen with an orange bar at the top.
Okay, that's not right. Oh, well. Phooey. All right.
If you
well,
press start
talk amongst
slideshow, we're good
yourselves.
to go.
You would think. That's weird. We're on the wrong slide. Okay. How about this? Are you seeing 4 books across your screen now? No. I think it's just sharing the wrong screen.
We're seeing the presenter view now.
Yeah. Let's see. Okay. How about now?
There you go.
All right. Good deal. Okay. So, as Rob said, I'm Michael Burnette, AF7KB, and this is How to Hammer. No, it's not. It's the completely wrong presentation. That's the problem. That's the presentation I'm working on for Pacificon next week. Now I see what has gone hopelessly awry. Man, I'm sure glad we got this professional guy in here to do this. How do we like me now? Should be a black screen. And
Black
now it should say
screen,
the
fast track to understanding.
ham radio antennas.
You got it.
Got it? Hooray! Okay, now, as Rob said, I'm Michael Burnette. I authored this series of ham licensed learning programs and a whole bunch of other titles. And I'm also the author of the soon-to-be published book, which has the same title as this program. What a remarkable coincidence. I don't think there is a single category of equipment in ham radio that causes more joy, more consternation, and sometimes more complete bafflement than our antennas. So let's see if tonight we can shed a little rationality on a topic that often seems like a lot of black magic. So time is short today. Here's what we're going to cover. We'll talk about how the signal turns into a propagating electromagnetic wave. We'll hit some basic electrical characteristics that come into play in antenna science. We'll touch on impedance matching, why it's important, and how it's done. We'll hit dipole antennas, monopole antennas, how directional antennas work. My goal here today is to give you a good basic framework for thinking about antennas. In fact, that's the goal of most of my work. It's not to turn you into an instant antenna engineer, as fun as that might be. This won't be the Every Antenna Ever Created presentation. That's a book, and it's already been written, and the League will very happily send you a copy for a mere $50. This also won't be the stupendously difficult math presentation. Many technical books on antenna theory don't seem to be able to make it more than a couple of paragraphs without lapsing into something like this, which is some lovely calculus. Why is my cat sad, I wonder? But really, this is not necessary for getting a signal from your shack to somewhere useful. Now, since someone is bound to ask, that is a real formula, and it's the formula for total power radiated by a theoretical point source when fed by a sine wave power source. In other words, it's completely useless. So what is an antenna? Well, an antenna is a transducer, and it converts electrical energy into electromagnetic energy. It's also, or at least you hope it is, an impedance matching device that matches the output impedance of your transmitter, should be about 50 ohms, to the input impedance of the universe, known as free space, which is about 377 ohms. Yes, the universe has an input impedance. Now, Maxwell's equations, shown here for entertainment purposes only, tell us that it should be possible to create an electromagnetic wave that will propagate through space. They don't give us any information on how to create that wave. So from the time Maxwell published the equations, it took 16 years before Heinrich Hertz worked out a way to send and receive those waves. Now here's one of Heinrich's experiments. This is the receiver. It consists of a coil hooked up to a spark gap. That's it. The stuff on this table is the transmitter. It's a spark gap transmitter fed with a resonant circuit. Now, here is Heinrich's antenna. He was working on frequencies right around 50 megahertz, our 6-meter band, and that antenna looks to be a slightly short, half-wavelength dipole with what we would call capacitance hats out here on the ends. In other words, Hertz had already figured out how to make an effective resonant antenna, and the basic principles have not changed one bit since he was in that laboratory. So here's what was going on in Heinrich's antenna and what's going on in your antenna. We energize the antenna with negative voltage on one terminal and positive on the other, or maybe ground on one terminal and positive on the other. The negative voltage pushes electrons away, the positive voltage pulls electrons toward it, and we have current flow. Now this current flow can't go on forever. That is, after all, an open circuit. Now ideally, just as the charge reaches one of the dead ends, the charges reverse, and the current flow reverses. As the current flows back and forth through the antenna, It jostles electrons in their orbits, which causes them to radiate an electromagnetic wave. Mark Twain once wrote, "Thunder is good, thunder is impressive, but it is lightning that does the work." When we think about antennas, we might say something similar. Voltage is good, voltage is impressive, but it is current that does the work. See, it's current that jostles those electrons and upsets them and makes them radiate electromagnetic waves. That's why we want to maximize current flow in our antennas. At that instant where the current flow is zero, in the middle of the flip of positive and negative, right there, that's where the magic of radio really happens. See, up until that instant, we're just Andre Ampere making a compass needle move next to an energized wire with DC, and that effect doesn't cover a lot of distance. It's interesting, but that's about it. But at that zero crossing instant, the electric and magnetic fields around that wire detach from the wire, and they take off through space. And just like that, we have a self-propagating electromagnetic wave propagating its way off to infinity. Now, I mentioned that an antenna is an impedance matching device, matching the output impedance of your transmitter to the input impedance of free space. And that term, free space, is one you're going to run into a lot in the world of antennas. What in the world does it mean? What are they talking about? Well, technically, free space is a space with zero electromagnetic or gravitational fields. In other words, something like the isotropic antenna, it's something that doesn't exist, but is useful for doing the engineering math. Now, practically speaking, we can say free space is a space around an antenna with nothing electrically significant in the near field of the antenna. That raises the question, what's he talking about, near field? What does that mean? Well, the near field is the area around the antenna where a lot is going on with the non-propagating fields around the antenna. Remember, until we cross that 0 point, the field isn't propagating. So if a conductor shows up in that near field, it's going to have significant effects on the antenna's impedance, and therefore on its effectiveness as an impedance matching device. In the case of directional antennas, that's taken into account in the design. In the case of dipoles, the best practice is to keep that near field clear of conductors, including the surface of the Earth. This is why one of the least common sentences in all of ham radio is, "My antenna is too high." Nobody ever says that. Generally speaking, the more you can keep your antenna's near field clear of extra conductors, the closer that antenna is going to perform to those wonderful specifications from the manufacturer or the designer. If your antenna is not performing the way you want it to perform or the way you think it should perform, the first place to look is in that near field. So, where is this near field? For antennas a half wavelength long or less, 1 wavelength out is the near field. For antennas longer than a half wavelength, the formula is 2d squared over the wavelength, where d is the antenna length. For a full wavelength 40-meter antenna, then, that works out to 160 meters. So you have to keep 160 meters around a full wavelength 40-meter antenna clear in order to have it really function well. That is one reason full wavelength transmitting antennas can be more than a little impractical. So, for a simple piece of wire or rod, an antenna certainly has a lot going on, electrically speaking. There are 4 key parameters that affect antenna performance. First, There are two distinct types of resistance, neither of which you can measure with your rusty trusty ohm meter. There's radiation resistance and there's ohmic resistance. Now, radiation resistance is the resistance that reflects the work done in radiating the signal. We want radiation resistance to be high relative to ohmic resistance. Now, ohmic resistance represents the amount of applied signal that just gets turned into heat. It's just like regular resistance. The ratio of radiation resistance to ohmic resistance determines the antenna's efficiency. Then there's the antenna's capacitance and its inductance. More accurately, I should say its capacitive and inductive reactance. Okay, need to take a quick detour here, the relevance of which will be made clear later. So capacitive and inductive reactance throw voltage and current out of phase. We're kind of getting into extra class stuff here, but hang in there with me. So because, say we hit a coil, we're hitting an inductance. Because the coil acts like a resistor during this phase here, this part of the cycle, see, it's charging up, and so it resists the flow of current. No current flows. But eventually, the thing peaks out, it starts collapsing, the field starts collapsing, and then current flows. So the current, we would say, is behind the voltage, or we'd say the voltage is leading the current. But I think more relevant for antennas, we can say the current is delayed in time relative to the voltage. That's really important. Now, through a capacitor, we find exactly the opposite effect. As the cycle begins, current flows easily through the capacitor, or at least it behaves as if it does. So there's virtually zero voltage across the capacitor. It's acting almost like a straight wire. As the capacitor fills up with charge, the current decreases, the voltage increases. So in this case, the current is leading the voltage. That's less significant in antenna design than the delay of current, because remember, it's current that makes the signal. Now, for a very, very long time, electronics students have memorized these phase relationships with the immortal phrase, Eli the Iceman. So across an inductance L, voltage E leads current I. So that's Eli. Across a capacitance C, current I leads voltage E. So that's ice. And here is a picture of Eli the Iceman, an actual photo. If you look closely, you can see that Eli's Ice Company was owned by Roy G. Biv, who's another famous fellow in the world of electronics. So in an antenna, we find radiation resistance, ohmic resistance, capacitive reactance, and inductive reactance. And all that combines to create the impedance of the antenna. Now, impedance is opposition to the flow of an alternating current. Impedance does not necessarily contain any reactance. It can be purely resistive, in which case we call it a simple impedance. If reactance sneaks into the picture, we call it a complex impedance. Our goal, usually, for our antennas is to have them be, or at least seem to be to our transmitter, purely resistive impedances. Hang on a second. How in the name of Hiram Percy Maxim did capacitance and inductance get into this straight piece of wire or rod anyway? Well, here's a dipole. Two relatively straight pieces of wire. Doesn't get any simpler than this. Here we have a conductor, and here we have another conductor, and it's separated by an insulator. Well, what do you know? It's a big old capacitor, and capacitors make current lead voltage, and they tend to block low frequencies while passing high frequencies. Okay, where's the inductor? I don't see any coil in there. Well, since there's alternating current flowing through that wire, there's a magnetic field expanding and contracting around that wire, creating inductance. Even though it isn't a coil, that wire is still an inductor. And inductors, of course, are the opposite of capacitors. They tend to pass low frequencies, block high frequencies, and of course, Eli the Iceman, right? They make voltage lead current. So, the equivalent circuit of what looks like an innocent couple of pieces of wire is actually something like this. We have a couple of resistances, some capacitance, and some inductance, all in series with a source of AC. And that all adds up to a series resonant circuit. If the applied signal is lower than the circuit's resonant frequency, the capacitance tries to block the signal. If the applied signal is higher than the circuit's resonant frequency, the inductance tries to block the signal. Right at the resonant frequency, the Goldilocks just right frequency, the capacitance and the inductance balance out, and the antenna presents its lowest possible impedance. That's when maximum current flow happens, and remember, it's current that makes the signal. Now, the exact same equivalent circuit could represent a monopole antenna, like a quarter wave vertical on your car, where one side of the dipole is replaced by a counterpoise or ground radials or by the roof of your car. You still get maximum current in the system when the system is operated at its resonant frequency. This is why the license exams at every level focus so much on how to create resonant antennas. Should mention, though, that there are non-resonant antenna designs that work perfectly well. I have one in my backyard about 30 feet away from where I'm sitting. If you pass radio frequency electricity through a conductor, it will radiate electromagnetic waves if it at least has a little bit of length to it. There is no rule that says it has to be resonant. Now, these antennas do require some sort of impedance matching device, and sometimes more than one, to make them work correctly. One reasonably common ham radio antenna that is a non-resonant design is the rhombic antenna. It looks something like this. It operates over a wide range of frequencies, and that's typical of non-resonant designs. And they can be set up to be bidirectional or unidirectional. We're going to focus on resonant antennas here today, though. When we talk about impedance, we're really talking about the ratio of voltage to current. That's not a figurative or a metaphorical ratio. Impedance is quite literally equal to E over I, just like resistance. When you hear something has high impedance, then, that means it has relatively high voltage and low current. Low impedance is the opposite. Knowing that, let's take a look at current and voltage in a dipole. Here it is. The current is shown in blue here, the voltage is in red, and you can see it in the center, and in the case of this antenna, that's also the feed point. The impedance is relatively low. We have lots of current, not much voltage. As we travel out to the ends here, that picture reverses until we have maximum voltage and minimum current at the ends. So the way we at least hope that works out, right? The impedance there in the center is about 50 ohms. But if we move that feed point, the feed point impedance will be higher. That's how we ended up with a design called the off-center fed dipole, or the OCFD, also known as the Windham antenna. The OCFD has a feed point impedance of around 300 ohms, simply because of where that feed point sits. So it needs to be fed with 300 ohm feed line with a matching device of some sort at the transmitter end or something. Some kind of matching has to go on with that. From the time we study for our very, very first license, we have beaten into us that we are to match the impedance of the antenna system to the impedance of the transmitter. Why? Why is that? Well, there are two reasons. First, to transfer maximum power from a source to a load, The impedances of those loads must match. There's a thought experiment, much beloved of electronic engineering students, that demonstrates this. Imagine a circuit like this one. This is a circuit that contains a battery and a couple of resistors. We're going to leave inductance and capacitance out of this picture. Just complicates matters. We'll just imagine we have a purely resistive impedance. R1 on the left there represents the internal resistance of that battery. The battery and the resistance constitute the source. Now, why are they the source? They are the source simply because we say so. That's really it. R2 is the load. Why? Again, because we say so. We connect an imaginary voltmeter across R2 and we set up an imaginary ammeter to measure the current through the circuit. So imaginary meters are very inexpensive and easy to store. I recommend them highly. Then we start substituting various values of resistance over here in R2, and we do lots and lots of Ohm's law and Joule's law calculations to determine the amount of power being dissipated by R2. By the way, if you're teaching ham classes and you're even a little sadistic, this is a very satisfying exercise to drill your students on Ohm's and Joule's law and teach impedance matching at the same time. Now, we're not going to go through all the calculations here today. You'll have to trust me, or not, when I tell you that with this setup, the maximum power transfer will occur when R2 equals 1,000 ohms. Now, here's a graph of the results, and you can see there's a pretty dramatic peak right here when we hit a matching value for R2. So power transfer is one reason we want to match impedances. The other reason to match impedances, of course, is to lower our SWR, our standing wave ratio, or our voltage standing wave ratio, as engineers like to call it. Lowering SWR is really not so much about effective power transfer as it is about avoiding having your transmitter automatically lower its power to avoid melting its final transistors. It's not a good result. So what is the source of SWR? Where does it come from? Well, the simple answer that's taught in most license courses, including ours, is that when impedances are mismatched, power gets reflected back to the source, mysteriously, and that reflected power is what smokes our transistors. And that is true so far as it goes, but I think you will agree that that explanation has a certain amount of pay no attention to that man behind the curtain to it. So here's a little deeper dive into the mysteries of SWR. Here are the culprits right here. These are what make SWR. See, neither capacitive reactance nor inductive reactance radiate power. They store power, they don't radiate it. When that power doesn't get radiated, it has to go somewhere, and the only somewhere that's available is the output of your transmitter. Now, if that's still a little vague for you, we're going to take this about as far as we can without getting into some pretty hairy math and vector diagrams and all that stuff. So we'll go back to this picture of the voltage and the current in a dipole. This picture shows what's called the incident wave in the antenna, the forward wave, the wave going out from the transmitter. Now, by the way, this picture tells you nothing about polarities. It just shows gross amounts of current and voltage at each point on the antenna. So let's take current out of the picture just for clarity's sake. And while we have the graphics program open, let's show the polarity of that voltage with the antenna wire serving as our 0 point here. Now you are much better informed, I suppose. Now, I said that's the voltage of the incident wave, the forward wave, which kind of heavy-handedly implies that there must be some other sort of wave that isn't shown, and that is in fact the case. So here's a basic rule. Every resonant design antenna whether or not it's being operated at the resonant frequency, contains an incident wave, a forward wave, and a reflected wave, or a reverse wave. And they are standing waves. In other words, the peaks and valleys of the waves keep arriving at the same points along the conductor, and if you could see them, they would seem to be standing still, even though they're actually moving through the conductor at the speed of light. If you've ever plunked a string on a guitar, you created a standing wave in that string. In fact, someone caught a kind of remarkable picture of those waves. It's a real picture. And something very similar is going on in your antenna, only with electrical waves and not acoustic waves. All right, when that antenna is exactly the resonant length for the applied frequency, the reflected wave matches up with the forward wave, and the feed point is what we would say is a happy, happy place. So here comes the reflected wave in green, and oh, perfect. 1-to-1 SWR, something actually seldom seen in the wild. If the antenna is too long or too short, though, the reflected wave arrives late or early. And now we have a less happy feed point because there's more voltage than there should be right here. The ratio of the reflected voltage to the forward voltage is the voltage standing wave ratio. Now, by the way, you might notice that if that reflected wave arrives late enough, it matches up with the forward wave again. And this is why every antenna has multiple resonant frequencies. You might have noticed that many of our HF bands are harmonically related. We have 180 or 160, 80, 40, 20, etc., etc. This is why. That's no accident. All right, now this, of course, is what we all call an antenna tuner. Not a tour, a tuner. It's the worst name for anything in ham radio. This device, wonderful though it may be, does not tune antennas. No amount of knob twisting on this thing will turn a 10-foot piece of wire into a resonant 80-meter antenna. I'm sorry. What this box does do, and does very well, is deceive your transmitter into thinking that it's feeding a 50-ohm load. That way your transmitter's protection circuits don't kick in, and you pump your full wattage into the antenna, minus, of course, any losses inside this box. Functionally, this thing is just like a transformer. So let's imagine we have a transmitter with 50 ohm output impedance going into a 300 ohm antenna. Well, we could match up those impedances with a transformer with a 6-to-1 impedance ratio. 6 impedance over here to 1 impedance over there. And we don't often use transformers for this purpose in our shack because they're expensive, they're lossy, and they're not very adjustable. Antenna tuners are far more versatile. And that gets us to the topic of directional antennas, also known as beam antennas. Probably the most popular is the Yagi antenna on whatever band. Most directional antennas work on the same principles, so we're going to look at the Yagi. Here's an HF Yagi, probably a monobander for 10 or 15 meters maybe, or something in that neighborhood. If you look closely, you can see some what are probably loading coils in the elements, which lets them be shorter at the expense of some efficiency. Now, those also might be traps, which are a whole different thing and would allow this to be a multi-band antenna. Just don't know from looking at it. Now, remember, an antenna that is too short is capacitive, so to cancel that out, we can add in some inductors. Once they finish raising the tower, you can see this is a crank-up tower and they've got it about halfway up, the antenna will send signal in this direction. So the back of the antenna is facing us and the front is facing away. The element in the center is the radiator. It's a dipole. The slightly longer element at the rear here is the reflector, And the shorter element at the front is the director. So this 3-element Yagi is going to have around 6 dB of gain. Each director element that you add adds more gain, but each one that you add adds a little less than the one before, so you reach a point of diminishing returns. By the way, this radiator is the driven element. That is what is connected to your transmitter. These others are not connected to the transmitter. Now, here is a Yagi with 26 elements. It's a stacked Yagi. It's made for the 2-meter band, and it claims 17 dB of gain. And in terms of practical antennas, that's probably pretty close to the limit until you get into the gigahertz frequencies where things get conveniently smaller. Well, how do these contraptions work? Well, as in so many electronic things, it all starts with Michael Faraday. Of course, he discovered that passing a magnetic field over a wire creates a voltage in the wire and then a current and vice versa. In other words, he discovered inductance. In the Yagi antenna, the radiation from the driven element, the radiator, induces a current in the passive elements, the director and the reflector. Now here we have what I feel is a very artistic representation of a 3-element Yagi. We'll energize that center-driven element. That wave starts traveling through space and it encounters the director element. It induces a current in that element which creates another wave. Because of the spacing between the elements, and because that director element is a little short, so it's a little capacitive, the new wave is in phase with the first wave. So they add together, and now we have a new bigger wave headed in the forward direction. It's that big purple one in the picture. Meanwhile, at the back of the antenna, something similar is happening. The wave from the radiator encounters the reflector. Now that reflector is cut a little bit long, so it is inductive, and here comes the point of all that diversion into reactances. The current in it is just a bit delayed. So the wave that leaves the reflector is out of phase with that first wave. On paper, they add up to 0. In practice, well, the wave going out the back of the antenna is significantly reduced. And that's how a Yagi and almost all other directional antennas does the magic. Here's a cool animation I found on the web that shows that in animation. Here's the driven element, and the signal from it is shown in red. Here's the director up here in blue, and that signal's in blue. And then here's the reflector doing its thing, out of phase with that first signal, and green is the resulting signal. All right, here's a type of directional antenna that does not work on quite the same principles as the Yagi. It is the parabolic reflector antenna invented by, does anybody know? Didn't see any hands go up. I was surprised. This guy, he's back. Heinrich Hertz was the inventor of the parabolic reflector antenna. He had them set up right there in his laboratory. The principle of the parabolic reflector is that the parabolic reflector concentrates received signals at the parabola's focal point. Of course, in transmit mode, signals originating from the focal point get reflected into a concentrated beam that goes mostly in one direction. Now, the gain of the parabolic antenna depends on the diameter of the parabola. Bigger dish equals more gain. Parabolics are not too practical for us on most of our frequencies. The minimum diameter of the dish is 1 wavelength. So even a dish for the 10-meter band would need to be at least around 33 feet in diameter. For higher frequencies, though, they're hard to beat for gain. So yeah, that has to be 1 wavelength across. The dish network dishes that you see littering rooftops everywhere operate in the 12 gigahertz range with wavelengths about half, or rather about an inch. Those dishes are a little shy of a meter in diameter, and if we run the numbers, they're producing somewhere in the neighborhood of 70 times gain. 70 times. That's about 18 dB worth of gain. That's how that system manages to work. It's not bad for a piece of gear that's so cheap they'll leave it on your house when you cancel the service, which they did. That's my roof. Well, that is about as much as I can pack into this much time, and it's a terrible death to be talked to death, so I hope I've covered some stuff that was interesting, and I will be delighted to answer questions in the time that we have left. And hopefully I've stopped screen sharing now. Speak up if you got a question, or raise a hand.
I've got a question.
Scott.
This is a dumb question, Michael, perhaps, or maybe it's rhetorical just for the whole group.
Good, I can do those.
Yeah.
If you ask a smart question, I'll probably just keel over.
So is it the voltage or is it the current that causes RF burns if one touches an antenna while it's transmitting, particularly at the end where there might be a high voltage, let's say?
Well, much as in electrical shock hazard, it's the current that's your enemy. You can we've probably all seen when you see the Tesla voltage demonstration, that's millions of volts. Doesn't burn your finger unless you hold it there for a long time. It can work up a little bit of energy, but a short zap off of that won't bother you at all, because there's nothing for current in it. It's all volts.
So it's like the old electrician's thing of it's volts that jolt, but it's mills that kill. So milliamps can kill you. Okay, thank you.
Yeah. Other stuff? Come on, Michelle. I must have baffled you somewhere along the way. Going once, going twice. All right. Well, listen.
Hold on. I got a dumber question. I can't let Scott beat me at this.
Okay.
If your SWR on your dipole is high, is it too long or too short?
Yes.
I win.
Yes, because of that thing that I explained with the SWR. It can be too long and you'll have a high SWR, or too short and have a high SWR. But one way or the other, you're not at the resonant length. So
Will
what
one
is
of
your
them,
SWR?
will one of them give you a higher SWR? Okay.
No, it will look exactly the same.
Okay. Thank you.
Now, however, if you have an antenna analyzer, that'll tell you if the antenna is too long or too short.
Yeah.
It'll tell you instantly.
I don't know about the instant, but
in the club.
I don't know about instantly.
No, it's instant. Yeah, it is instant. You hook it up, and as fast as you can switch it on, it tells you your antenna is too long.
It doesn't tell me. Mine doesn't tell me that. What kind do you have? Mine doesn't say that.
You got one of those good old MFJ fighters that looks like it was designed for the 60s space program?
Yeah.
I shouldn't say that. Those guys are so good to me. They let me use pictures of anything I want in their catalog. That's terrible of me. You have an MFJ. It should tell you should have a way of finding the resonant frequency. You can go back to that instruction book. That thing tells you more than you think it's telling you.
Okay, back to the instruction book. I've heard that before. Thank you. Okay. I just wanted to beat Scott. That's all.
Hey, Bob, I'm gonna come to your house and let the dumb lead the dumber.
Somebody take a rig expert over to Bob's house and show him a real antenna analyzer. Those things are amazing. Got a little screen, Bob, and it gives you more data than you ever wanted about your antenna just instantly.
I got one of those little
Made in the
small.
Ukraine, too.
I got one of those little small gizmos, VNA gizmos, but we need to have another talk on how to operate it.
Oh yeah, yeah. So you got one of those $35 specials from China?
Yeah. With the Smith chart that everybody
Yeah.
forgets out. Everyone forgets about the Smith chart after your novice exam.
Yeah, isn't that thing? That is so fun. I have one of those too.
It's great. It's great.
That's a great deal.
It's great.
So switch it to Smith chart, and it'll start giving you some good clues.
Mm-hmm. I forget how much I paid for my
Anything
spectrum.
else, folks? All right.
Okay.
Well, so thanks for having me at your meeting, folks. It's a tough time for clubs. I notice going around the country, and I know for our club, it's been a very challenging time. So we're certainly in rebuild mode, and I wouldn't be surprised if you are too. Keep doing the good work. Remember, we're doing important stuff for our communities and for the new people in the hobby too. I say in my technician book, in the first chapter, you don't realize it now, but one of the reasons you're getting your license is so you can join a ham club. And I really mean that. I think what we do is just fantastic. So keep up the good work, and if I can help in any way, by all means, let me know. Thanks, folks.
Thanks a lot. We all appreciate this.
All right, Michael,
care.
thanks. Yeah, this was a light night for us, unfortunately. We usually get into the 30s, so this was a little surprising. I don't know, there must be something going on tonight, but it's the start of the Halloween season, I guess. So everybody's out doing things. So
I'm going to go grab lunch with my wife before she goes off to lead her YL net tonight. So
all right,
I'll see you guys later.
thank you very much. You have a good evening. Well, that was quick. All right, guys.
Very informative.
Yeah, thanks for showing up tonight. It was a light night on participants, but that's all right. It was quality though. That's quality over quantity. So, anybody have any questions for the board or anything like that? Anything you've been wanting to know about the club, or any suggestions or comments? Anything to help us make the club what you want it to be?
Hey, John, I'm the worst club member in the whole club, I know, but I just sent in my, because I'm never here, but I just sent in my renewal dues for next year. So I'm paying even though I'm never here.
Hey,
So,
that's the best kind of club member.
yeah, my heart is in there. But anyway, I'm still a working schlub.
Yeah,
So
well, thank you for supporting the club. It goes a long way to help with the repeaters and a lot of other things that we do behind the scenes. So thank you for supporting the effort. You just need to get to the meetings more often too.
This is Michelle. Have you worked with the Nano VPN meter at all?
Bob's got one, I think.
Yeah, I've got one.
And do you recommend those? And how often do you use it?
I don't use mine very often. I got it for a specific purpose. What I had some antennas that are outside the frequency range of my MFJ tuner, most notably the 70 centimeter band. And I wanted to check the SWR in the 70 centimeter band. And also I've got a 220 radio. So I needed something to check those, check the SWR on those. And that's what I bought it for, and it served its purpose. How often do I use it? And maybe twice a month, maybe, when I'm doing some antenna work. But essentially, I get the antennas up, they're resident, and I'm happy with them.
hey, Michelle,
For $35, it's a good investment.
Thank you, but would you recommend everyone get one of those early? Is that like the first purchase you'd recommend as far as antenna analyzers?
Hey,
Was it-
Michelle, before you buy anything, I think the North Fulton Club or the Gwinnett Club, or maybe our club here had a program on the Nano VNA that's on a
All right.
video. And if you search their websites, you might want to watch the video program about using a Nano VNA before shelling out cash. I've
Right.
never had an antenna analyzer, and I've been a ham for 30 years maybe and built loads of antennas.
Wonderful. Thank you for that.
Hey, I don't know if Bill's with us. I see him on the screen. Any thoughts on antenna analyzers, Bill, especially for a newbie?
Well, can you hear me? Let's make sure my
Yes,
mic's
yes,
working.
yes.
Yeah, if you're going to get into building and whatnot, it's a valuable tool to have. The micro VNAs, I actually have played with those. I think they're a bit complicated for the kind of stuff we're doing. Right now, I'm playing with the little MFJ 226, which is about $125. It'll graph pretty much anything you want to graph. To me, that is the ideal one to use at home and carry. MFJ 259 requires some of them require 10 AA batteries, some require 8 AA batteries. The little 226 requires 2 AA batteries, so you can carry extra batteries with it. It's worth it if you're going to do a lot of building. If you're not, it might be more practical to borrow one from somebody.
Thank you.
I think Bob's got one of the nanos up.
Yeah, that's it. Yeah, like I say, it was fun to play with, but I found trying to manipulate that little knob on the side in the menus you had to go through made it a little bit more complicated than my old eyes can see. If I have to carry a pair of glasses with me, it's too small.
Well, there's software, there's some software for it, so you don't have to worry your eyes. You can,
so you're saying I need to carry a laptop instead of eyeglasses?
yeah.
Okay.
Yeah. It'll work a lot better. I'm still trying to do it on my Raspberry Pi though.
Oh, okay. No, that's my 2 cents worth. The least I have to carry and lose, the better I am.
Yeah, like Scott said, we did a program on nano VNAs. I think it may have been the middle to the end of last year, if I remember correctly, but should be on our YouTube channel. So I want to say probably, I don't know, Rob may run off, but I don't know, September, October, maybe last year. But that was I think Bob was asking a lot of questions in that particular forum. So
yeah, and he was very. I emailed him, and he really gave me a lot of good hints for me to get it up. But the thing is, like so many things, you have to use it. You got to use it so you remember the menus. But if you have it and you use the software, the computer software for it, the programs are freely downloadable. That makes it a lot easier, and you can save stuff. You can save routines and things like that. Save the measurements on your computer to make life easier for you.
Yeah, to be fair, I should qualify that, I guess. Everybody knows me. 90% of what I do in the field somewhere outside. I don't operate that much from home. So Bob, exactly correct. If you're working from home and you've already got the laptop, those little micro VNAs are really nice to have. For my use, they're too small to carry in field. That I should have qualified that when I said it. Sorry about that.
Something too small for the field.
Well, yeah, I mean, if you get them up there and I can't really see them, and then every time I try to use the thing, I have to reprogram. But Bob's right. If you've got it on a computer and get to it that way, yeah, they're nice.
Michelle, I'll say again, I've never used anything in all these years, and basically I cut something roughly to resonant length and then use a little, and I'm mostly a QRP operator, so how much current I'm getting out is important, but still I've worked people with just handmade antennas, never measured, worked with 1 watt and 2 watts, 2.5 watts, and heaven forbid 5 watts, and worked people all over the place. So it's just not that critical. One of my old buddies used to, his main hobby was loading up everything he could with whatever tuner he had, bed frames, the refrigerator. Not the gas stove, thank God. The picture window frames, screens, wire fences. I think I've made a contact with that guy on everything possible at his house. And they just, if you can get something to resonate or, emit electrons or the electromagnetic wave, it doesn't have to be perfect unless you're going for some super contest station. So I always say, don't spend lots of money, but have lots of fun.
Thank you very much.
I think Bill kind of hit it on the spot too. If money's tight and especially if you're new and you're not really into building a lot of stuff, it might be in your best interest to hold off on actually purchasing and just borrow and for the time being. And then when you feel the need, then you can go out and purchase one or find one at a Hamfest at a good deal.
My big focus is learning. So if it'll help me learn, I'll get it.
I think if I can add to that, I think there is, John said, there are a lot of antenna analyzers around. I mean, they're pretty readily available. So I'm sure you could borrow one and try it out before then. And a comment about the old, I think Bill mentioned the MFJ 259, which is was the old standard, I guess. And it uses a lot of batteries, and it's a little larger than some and kind of clunky, but
Bob's got one on the screen there.
Okay, it is the old workhorse, and it does an amazing amount of work. And in fact, you can, if you look at the ARC YouTube stuff, you'll find a series of videos out there. Several years ago, we had Martin Jew from MFJ come and give a talk about the MFJ 259, and he went into great detail about all the things that you can do with. You can do amazing things with it, and in fact with most antenna analyzers. So might be worth watching a few of those too to get an idea about what you can do with one. But they're readily available. Try borrowing one.
I'll certainly do that. Thank you.
But like Scott said, if you just cut your antenna to the size in the article, you're probably going to get away with a reasonable signal.
Great.
I think many of us did that before we ever got. I mean, I did it for years before I bought an antenna analyzer.
Wonderful. Thank you.
Good luck.
All right, any other questions or comments or suggestions for the group?
Yeah, if anybody still has their TNC sitting somewhere in the recesses of their closet or back in the bottom of their basement, pull it out and get on 2 meters, 14571. We're trying to see if we can generate some more activity on the packet frequencies now. So if you got one, find it, pull it out, hook it up, let's use it. Or give it away at the next Hamfest. Thank you. That's it.
Thank you so very much. This is incredible.
All right. Well, like Rob mentioned, there's the Stone Mountain Hamfest coming up the 6th and the 7th, I think, of November, the first full weekend. Always a good opportunity to pick up that antenna analyzer, used or new. We've got Friday Lunch Bunch where we meet at the Brookhaven Mellow Mushroom. So if you hadn't had a chance to join us for that, please do so. And we're also, we've talked about in the past about trying to do a breakfast maybe once a quarter or something for those that can't do lunch. So keep an eye out for something like that possibly coming up in the next month or two. And then, of course, I mentioned the Stone Mountain Highland Games special event station next weekend. Keep an eye on your .io group, the ARC IO group, for information on that, and we'll post something on the web too. And then, of course, we'll have more stuff. We're going to try to get on the calendar and get it so that you see it months in advance and can plan for it. So please do join us when we do some of these outings. especially when Bill's there, Bill brings out he's used his guy's antenna analyzer. So if you want, if you got an antenna you've been working on, bring it out, and I'm sure we can hook it up and check it out for you and see how things are working. It's a good opportunity to bring a new radio out you might have, or especially if you're a newbie, and get some suggestions from folks, hook it up and see it, get it working properly. So do join us when we have some of these weekend events in the park. They're typically on the north side because a lot of our club is oriented there versus downtown, but we've tried to spread things around a little bit. But keep an eye on the calendar, and got a whole 12 months of activities coming up. So we're gonna be busy. So there'll also be a sign-up sheet coming out shortly for manning the table at the Stone Mountain Hamfest for the club also. So it's a good chance to hang out for an hour or two and meet and greet and rag chew about the club. So join us for that also. Anything else? Anybody got any other comments, anything? If not, don't forget tomorrow, join us at Mellow Mushroom, and worst case, if we don't see you again for 30 days, join us again for this same Thursday night, first Thursday night of the month, 7:30 here on Zoom, I believe. I don't know if we'll be back to in person yet. Since we've only got really one more month to go, we may just do Zoom for November and then do the party in December at a restaurant, and then get back to in person in January. I think we've got all the bugs worked out at the Red Cross with the internet connection, so we should be able to meet down there and have a good Zoom connection too. So that's been one of our major problems in the past. Plus getting access. They changed the way we do access at the Red Cross. Normally there was a security guard and we showed up and had to be out by 9, but now it's the volunteers got to let you in. So we got to have a volunteer that's a member of the club basically to let us in. So we're working on that. So that's been a little bit of a hindrance also. So, well, thanks for joining us tonight. Thanks again, Rob, for another great program. Rob, do we have anything in store for November yet? Are you with us? He may be out chasing his cat right now. Yeah, if not, just keep your ears pinned to the emails and the Facebook group and the website for what Rob has in store for us. And the coming months, program-wise, they've been really good. So thank you for joining us. Y'all have a good evening, and hopefully you can join us for lunch tomorrow. Y'all have a good evening.
Okay.
Thank
Thank
you.
you.
Good night. Thank you.